Hello everyone. So today I want to talk about Kirchhoff's current and voltage laws. Those two, along with Ohm's law, form the foundation for this entire course and all the different methods you will learn. So let's start off with Kirchhoff's current law. Essentially what Kirchhoff's current law says is that if you have a node, so any kind of node, and you've got wires that are coming out of it, and you've got currents that are flowing in, some that are flowing out. Essentially, what flows into a node has to come out. And so that's basically, it's kind of like similar to water flowing through pipes. If you had a place where you had a bunch of pipes joined together, obviously what flows in has to flow out. So that if you sum all the currents flowing into the node and all the currents going out of it, they should be equal to one another. A way that this is typically expressed, and it's a little bit more of a fancy way of, of expressing it, is that the sum of the currents entering or leaving, we could say, a node is equal to 0. So for example, you've got a node here. You've got 4 wires that are joining in on there. And let's just say that you ask the question, how much current is going into the node in every single one of these wires? And so let's just say you sum all these up. So you have I1, I2, I3, and I4. So I1 plus I2 plus I3 plus I4 is equal to 0. So you might say to yourself, like, wait, I thought if all the currents are going in, then how is that actually equal to 0? Well, remember what I said on the previous video when talking about signs. In circuits, we usually just assign a direction for the current. And then when we do the math, if it comes out negative, it means it's actually not going in that direction. So let's say, for example, let's say we know that I1 is equal to 1 amp, and then I2 is equal to 4 amps, and then I3 is equal to, let's say, 2 amps. So if these are all given, let's just say you know what those currents are, and you know they're all going in, right? We've specified all the directions here. The only current we don't know about is I4. So if we plug these numbers into that equation and solve for I4, I4 is going to be equal to negative 7 amps. And it's negative because we know that basically what goes into the node has to come out. It's just conservation of mass. And so you basically say, okay, let's sum all the currents that are entering into this node. Let's sum all them up, and then we went through the math, and then we figured out, oh, one of them is actually negative. And so again, that's kind of how signs work. You don't have to know the direction the actual direction of the current before you solve the problem. And so, yeah, a lot of times the typical way that this law will be described is that if you sum all the currents that enter a node, you sum all them up, it should equal 0 because they balance each other out. Some of the currents will be positive and some of them will be negative. What goes in has to come out. Another way you could do it is you could sum all the currents going out of the node as well, and then when you do the math, some of the currents will then come out as negative. So that again, that basic physical principle, what goes in has to come out, is true. So the next law that's very important, let me go ahead and create a new page here, is Kirchhoff's voltage law. So Kirchhoff's voltage law states that the sum of the voltages in a loop is equal to 0. So, for example, let's take a very simple circuit here. And let's go ahead and say that we've got certain voltage across this resistor. And then we also have a certain, we'll call this one V1, V2, and then we'll call this V source here, the voltage there. So essentially, what this law says is that we go around this loop and we sum all the voltages around in a loop, it should be equal to 0. So here's a tip for when you're going around these loops. What you should do is you can go any direction you want, but I'm just going to go clockwise here. The first sign that you encounter is the sign the voltage should have in your summation. So for example, as we go through this loop here, we're going to have negative Vs because we hit a negative sign there. Then we're going to hit a plus sign there, so plus V1. Then we keep on going, and then we hit another plus sign, so plus V2. And all of that is going to be equal to 0. And so if we then had certain values for like V1 and V2, we could solve for Vs or whatever our unknown is. So that's basically, that is Kirchhoff's voltage law. So what's cool about this law is that it works for any loop in a circuit, literally any loop. So you could have like a really complicated circuit, for example. Let's see. You'd have a much more complicated circuit. Let's draw another source here. And essentially we could do a KVL, Kirchhoff's voltage law loop, around any loop in the circuit. So we could go around here. We could do one. Whoops. There should be a backspace somewhere here, but here I'll just resketch it. We could do, so we could do a loop, we could do this loop, we could do this loop, any kind of loop that you can define in the circuit, and then you go around and sum up all the voltages across the different components, it will end up being 0. Now, the other cool thing about it too is that you can assign, just like in the currents, when we were solving for currents in Kirchhoff's current law, you can give the current a direction and apply the equation, and if it comes out negative, then that's okay, you just guessed wrong. And in the same way, all you do is you can, if you wanted to apply KVL to, let's say, let's just say this large, whoops, I did it again. Say you wanted to apply KVL to the larger loop here. So this one going all the way around. Let's call this VS1, VS2. What you could do is you could just go ahead and say, oh, this voltage here, I'm just going to give it this random direction and call it, let's see, I'll just call it V1 and then call this, I could give it the opposite direction if I wanted to, it doesn't matter, V2, and then I could say the voltage across this resistor is V3. So then, if I go around and do my loop here, again, I'll just go around it in a clockwise direction, and whatever sign that I hit first is the sign of the term in my equation. So I'm going this way, boom, I hit a minus sign. So that's minus VS1. Then I keep on going. Then I hit a plus sign, boom, that's plus V1. Then I continue and I hit another minus sign, that's minus V2. Then I continue and I hit a plus sign, that's plus V3. Then I hit another plus sign, the plus sign over here on the source. So that's plus VS2. And all of that should be equal to 0. So that's how you write an equation that governs that loop there. And we didn't have to, we can just arbitrarily pick the sign here because in the end, all the math will work out and it will give you the right answer. So Isn't that cool? I think it's cool. So hopefully that gives you a good introduction to Kirchhoff's voltage and current laws. And as we begin to work examples, I think it will become more solidified. So thanks for watching, and I will see you in the next video. Hello everybody, thanks for watching. If you found this content helpful, would you please consider liking and subscribing to the channel? That will help other people find it. And if you won't do it for me, will you do it for my cat, Muon? Named after my favorite subatomic particle, by the way. So, she will be very, very upset if you do not like and subscribe. So please, don't disappoint. How could you say no to this cuteness?